Welcome to Talk Tensors. If you've been paying any attention to the machine learning landscape over the last few months, you know the vibe has shifted.
Oh, it's palpable.
For a long time, the name of the game was scale, bigger parameters, bigger data sets, bigger clusters. And sure, that's still happening, but there's a new signal in the noise. We are moving away from models that just talk.
Right.
And we are moving toward models that actually think.
It is, I think, the single most significant shift we have seen since the original GPT moment. We are transitioning from rapid-fire token prediction, what we might call reflexive AI.
A gut reaction.
Exactly, a gut reaction. We're moving from that to deliberate, reasoned problem solving. If you've heard the buzzword System 2 thinking or seen the viral charts regarding OpenAI's O1 model, you know exactly what we are talking about.
It's the O1 moment. It really feels like we've crossed some kind of threshold. For years, large language models, or LLMs, have been these incredible improvisers. They're like that friend who can talk their way through any conversation, even if they don't really know the facts.
That's a great analogy.
But when you ask them to do complex logic or multi-step math, they often hallucinate or just crash and burn.
That's a very fair characterization. They were great at, fluency in language, but mediocre at best when it came to logic. They were what we're now calling level 1 AI, purely conversational.
And now?
Now, we are entering the era of level 2 reasoning. And this isn't just some marketing term or a branding exercise. We are seeing the rise of the large reasoning model, or LRM. And the fundamental architecture of how these models process information is changing from, a straight line to a branching tree.
So today, we are going to tear this apart. We have a massive stack of research, primarily centered around a really comprehensive survey on reinforced reasoning, alongside a ton of data on the open source attempts to replicate this tech.
Yeah, the community is moving incredibly fast on this.
So here is our roadmap for this deep dive. First, we are going to define what a reasoning model actually is. How does it differ from the ChatGPT you were using a year ago?
What's actually under the hood?
Exactly. Second, we're going into the kitchen to see how these things are cooked. We'll talk about process reward models and reinforcement learning, which is where things get really interesting.
Then we have to talk about the new scaling law. This is a big one. It's no longer just about training time. It's about test time scaling. Why does letting the model pause and think for 10 seconds make it smarter than a model that answers instantly?
I can't wait to get into that. And finally, we'll wrap up with some novel notions. Our speculative, I want to stress speculative, look at where this technology takes us next, from recursive scientific discovery to a completely new type of economy.
The core thesis we are exploring today is simple, but I think really profound. We are witnessing the end of the next token era and the beginning of the thought process era.
I like that.
In this new paradigm, the journey the model takes to get to the answer matters significantly more than the answer itself.
Okay, let's unpack this. We keep throwing around System 1 and System 2. This comes from Daniel Kahneman's behavioral economics work.
Yeah.
How does this map onto a GPU?
It's a perfect analogy. It maps almost one-to-one. Kahneman describes System 1 as fast, intuitive, and automatic. It's your gut reaction.
Like muscle memory.
Exactly. If I ask you what's 2 plus 2,
Yeah.
You don't calculate it. The answer 4 just appears in your head. That is System 1. Standard LLMs up until now have essentially been massive System 1 engines.
How so?
They are autoregressive. It's a fancy word, but all it means is they see a sequence of words and they probabilistically guess the next most likely one. They don't plan. They don't look ahead more than a single step. They just react.
Right. They are essentially playing a very, very sophisticated game of finish the sentence, which is incredible for writing an email or summarizing an article.
Absolutely.
But the issue is when you try to finish the sentence for a complex physics proof or a multi-step word problem, probability isn't enough. You can't just guess the next step of a derivation based on, vibes.
Precisely. That's where you need System 2. Now, System 2 is slow, deliberate, and logical. If I ask you what is 17 times 24, you can't just know the answer.
No, I definitely have to stop and think.
You have to stop. You have to allocate cognitive resources. You have to visualize the numbers. You multiply 7 by 4, carry the 2, and so on. You are executing a multi-step algorithm in your head. That is reasoning. That is what we are now trying to teach AI to do.
And technologically, how do we force a model to do that? Because usually you type a prompt and the tokens start streaming out immediately. It feels like the model is just blurting out the first thing that comes to its mind.
That's the old way. The breakthrough here is introducing the concept of thought tokens, sometimes called a scratch pad.
Okay, thought tokens.
Instead of jumping straight to the final answer, The model first generates a sequence of tokens that represent its intermediate steps. These are often hidden from the user, though sometimes you'll see it as a show your work feature.
So it's talking to itself.
It's effectively talking to itself, yes.
Right.
It's sketching out a plan, testing a hypothesis, maybe even realizing it made a mistake and backpedaling, all before it gives you the final output. It's an inner monologue.
So it's showing its work. Or rather, it's utilizing a scratch pad that we, the user, might not even get to see.
It's doing the work. That's the distinction. It's not just showing it after the fact. In the source material we're looking at, they describe this as moving from simple autoregressive generation to complex cognitive architectures like, tree search and reflective thinking.
So you're shifting the compute load.
You've hit the nail on the head. In a standard model, all the intelligence is baked into the model's weights during training. It's static. In a reasoning model, a huge chunk of intelligence happens at inference time while you wait for the answer.
Okay, that makes sense. But to teach a model, to have an inner monologue, you need data. And this brings us to the first major bottleneck discussed in all the research. We can't just scrape the internet for this, can we? I mean, the internet is full of questions and answers, but it's not full of people narrating their inner monologue while solving problems.
No, you absolutely can't. You're right. The internet is full of the what, but it's remarkably light on the how. It's full of final results.
Right, the answer is 42.
The answer is 42. But there's no record of the billions of wrong paths someone explored to get there. Even when you find step-by-step guides, they're often messy, or they skip steps because they assume the reader is smart and can fill in the gaps.
And a model can't fill in those gaps. Not at first.
Not reliably. To train a reasoner, you need pristine chains of thought. You need the model to see. Here's the problem. Here is the first logical step. Here is the verification of that step. Here is the next step. Over and over and over again for millions of examples.
And you can't just hire a million humans to write these out. I mean, I imagine that's the first thought everyone has.
You could, and people have tried. Human annotation is the gold standard for quality. There's no doubt about it. Humans are meticulous, they understand nuance, but it is prohibitively expensive.
The scale is just impossible.
Imagine trying to pay PhD-level physicists to write out step-by-step reasoning for millions of advanced mechanics problems, or paying senior software engineers to document their debugging process for every single bug. It doesn't scale. You'd bankrupt the company before you train the first epoch.
Okay, so if humans are too expensive and the internet is too messy, where does the data come from? This feels like a chicken and egg problem.
The solution is fascinating, and it's a theme we'll keep coming back to. AI annotating AI. We are seeing a shift toward what the papers call LLM-driven search algorithms.
How did that work? Is it just one model grading another model's homework?
That's a good starting point, yeah. There are two levels to this. The first, and simpler one, is outcome annotation, or outcome-supervised reward models, ORMs.
Okay.
That's the easier one. You give a model a math problem, it generates a bunch of steps and a final answer. You have a checker. Maybe it's a simple Python script for a math problem or a unit test for a code problem that just says correct or incorrect.
So it only looks at the very end.
Only at the end. If it's correct, you keep that data. You tell the model, good job, that was a successful path.
Okay, but that only tells you if the destination was right. It doesn't tell you if the map was any good. I could guess the right answer for the wrong reason. I could make two calculation errors that completely cancel each other out by coincidence.
Exactly. And that is why process annotation is the holy grail. This is where we use models, often running complex search algorithms like Monte Carlo simulations, to check every single step of the logic along the way.
Let's visualize this so the listener can really grasp it. The survey we looked at mentions an image with the simple arithmetic sequence, 6, 10, 14, 18. The question is, what is the 100th term?
Right. A classic middle school math problem. An outcome approach just checks if you got the final number, which is 402. That's it. Pass or fail.
And a process approach.
A process approach looks at step 1, where the model might write. The common difference is 10 minus 6, which equals 4. A separate verifier model looks only at that step and labels it correct. Then it looks at step 2. Apply the formula for the nth term, which is a plus, N1D. The verifier says, correct formula.
What if it makes a mistake?
Let's say in step 3, it plugs in the numbers and writes 6 plus 99 times 5. The verifier immediately flags that step as incorrect. The common difference was 4, not 5. The process stops. That entire reasoning chain is either discarded or, more importantly, used as a negative example.
So you're not just collecting successes, you're collecting a detailed map of all the dead ends.
Precisely. This allows us to build data sets not just of right answers, but of correct paths of thinking, and just as importantly, incorrect paths and where they went wrong.
That feels like a massive jump in data fidelity. It's a much richer signal. You're teaching the model how to think, not just what to say.
It is. It's the difference between memorizing flashcards and actually understanding the subject. It transforms the training data from a flat list of Q&A pairs into a rich branching tree of logic. And once you have that data, you can start doing some really, really interesting reinforcement learning.
Which leads us perfectly into part 2 of our analysis, training the reasoner. We've heard of RLHF, reinforcement learning from human feedback. That was the magic sauce behind the original ChatGPT, right?
It was. It's what made the models feel so aligned and conversational. But as we just discussed, it relies on humans ranking outputs. Is answer A better than answer B? And again, that's hard to scale, especially for complex, factual tasks.
So we're moving past that.
We are evolving toward RLAIF, reinforcement learning from AI feedback, which we just touched on, and also to more direct methods like DPO or direct preference optimization.
Okay, we need to define DPO for the listeners because it comes up constantly in the literature now. It sounds incredibly complicated, but the core concept is actually about simplification, isn't it?
Yes, very much so. Traditionally, reinforcement learning for LLMs was a two-stage process. First, you train a separate reward model. This model's only job is to look at what the AI did and give it a score, a reward.
So you have your main LLM and then a separate judge LLM.
Exactly. Then, in the second stage, you use that judge to train the main LLM, trying to get it to produce outputs that the judge will score higher. It's complex, it can be unstable, and you have to keep two huge models in memory.
And DPO changes that.
DPO simplifies this brilliantly. It removes the need for that separate explicit reward model. It just uses the preference data, the raw data that says answer A is better than answer B, to directly update the main model's policy. It's mathematically elegant and much more stable to train.
But here's the catch, and the sources are very specific about this distinction. Most of these methods, whether it's classic RL or DPO, have historically relied on outcome reward models, or ORMs.
Correct. And an ORM, as we said, is like a teacher who only looks at the final answer on your test. If the answer is wrong, you get a 0. You don't know why you got a 0. Did you misunderstand the question? Did you make a typo in line 1? Did you have a brilliant process but mess up the final addition?
And for complex reasoning, that is a total disaster. If I'm solving a 50-step coding problem and I make a single syntax error in step 2, the whole thing fails. An outcome reward model just tells me bad job, but it gives me no clue where I went wrong. It's what the researchers call a sparse signal.
Very sparse. There's only one signal at the very end of a long chain of actions. This is why the process reward model, or PRM, is the absolute game changer for reasoning. A PRM doesn't just grade the test, it grades every single line of the homework.
It provides what they call dense feedback.
Dense feedback. I love that term. It means there's nowhere to hide a hallucination. There's nowhere for a small error to fester.
Because the model gets a signal at every step. Good step, wait, bad step, stop.
And this allows the model to identify the first pit, a great phrase from the research, the specific moment where the logic derailed.
That first pit concept is so crucial. If you can catch the error immediately, the model can learn to self-correct during training. It doesn't waste time and compute hallucinating a further 10 paragraphs that are all based on a false premise from step 1.
And this creates a reinforced cycle, which is the engine of this entire field. The model generates reasoning data. The PRM scores it step by step. The model then trains on that scored data to get better at reasoning. Then, the improved model generates even better, more complex reasoning data for the next round.
It's a self-feeding loop of intelligence, a flywheel.
It is. This is how we escape the limits of human-generated data. We are bootstrapping intelligence using the model's own ability to verify logic. It's a really profound idea.
It's the engine of the large reasoning model. But there is another side to this coin. We've talked about training making the model smarter before we ship it, but the source material highlights a new phenomenon that might be even more important: test time scaling. This is the part that honestly blew my mind.
This is the new Moore's law for AI. It's that significant. For a long time, the scaling law was simple. More parameters plus more training data equals a smarter model.
And that's a capital-intensive law. It means you need to buy more H100s, build bigger data centers.
Exactly. It's scaling at training time. But now we have found a third variable that's almost independent: test time compute.
This is the idea that you can make a model smarter without retraining it, just by letting it think longer when you ask it a question.
Precisely, just like a human. If I ask you a complex riddle and demand an answer in 1 second, you'll probably give me a heuristic guess, your system 1 guess, and you'll probably be wrong.
For sure.
But if I give you 10 minutes, a piece of paper, and a pen to write it out, check your assumptions, and verify your logic, your effective intelligence shoots up. Your brain didn't get bigger in those 10 minutes, but your output got smarter. We're seeing the same thing with these models.
The sources mention a specific finding, a new scaling law. Accuracy increases linearly with the log of the compute time.
Which is a shocking result. It implies we haven't hit a ceiling. It suggests that if we let these models think for hours or even days on a single problem, they could solve things that currently seem completely impossible. We are trading time for intelligence.
But what is it actually doing during that time? It's not just sitting there humming, it's running search algorithms. This brings us to a term that I haven't heard since my college comp sci classes: tree search.
Right. It's not just generating a single line of text anymore. It's navigating a tree of thoughts. The root of the tree is the problem, and each branch is a potential step in the reasoning process.
And the sources outline a few key strategies here. The simplest one seems to be majority vote.
Also called self-consistency.
Brute force, basically.
Essentially, yeah. You ask the model the same question 100 times, but you turn up the temperature so it gives slightly different answers. You generate 100 different reasoning paths. If 80 of them lead to answer A and 20 lead to answer B, you pick answer A.
It works, but it's wildly inefficient.
It's inefficient, and it's just hoping that the truth is statistically more likely than any one specific hallucination. It's a good baseline, but it's not truly reasoning.
Then you have the chess computer approach, tree search, or MCTS, Monte Carlo Tree Search.
This is where it gets really sophisticated. MCTS is the core algorithm that powered AlphaGo to beat Lee Sedol. It's a very clever way to explore a massive search space.
How does it work in this context?
It explores different branches of reasoning. It looks at a potential step and asks, if I go down this path, does it look promising? If the answer is yes, it expands that path, exploring deeper. If the answer is no, this looks like a dead end, it prunes that branch and backtracks to try something else.
But how does it know if a path is promising? In chess, you have a clear win-loss condition. In a generic logic problem, how does it know it's getting warmer or colder?
That's the beautiful part. It goes back to the process reward model we just talked about. The PRM acts as the value function, or the heuristic. It scores the intermediate steps. So the MCTS uses the PRM as its compass to navigate the massive maze of logic. A high score from the PRM means this path looks promising. Explore more here.
So the PRM trained during the training phase is now being used as a guide during the inference phase.
Exactly. The two are deeply connected. And within that, you have more specific techniques like look-ahead search. Here, the model explicitly simulates tinier dollar steps into the future. It says, okay, I'm at step 3. If I make this assumption now, what will my state look like at step 8? It uses a reward model to evaluate that future state. If the future state looks like a dead end or gets a low score, it abandons that current thought before wasting any more time on it.
It's mental simulation.
Yeah.
It's literally thinking before speaking, implemented in code.
And critically, this entire process involves self-correction. This is maybe the most human-like capability. It's the ability for the model to generate some output, some part of its reasoning chain, and then have another part of the process look at it and spot a flaw.
Like an internal critic.
A very fast, very logical internal critic. It might spot a calculation error or a logical fallacy in its own work, and then it can trigger a backtrack and refine it before ever showing it to the user. This reflection step is what separates a reasoner from a chatbot. A chatbot often just doubles down on its error. A reasoner can fix it.
So we have the training paradigm process reward models, and we have the inference paradigm search and thinking time. Now, let's look at the real world. Who is actually doing this at scale?
Well, the benchmark right now, the one everyone is chasing, is clearly OpenAI's O1 series. The performance metrics that have been reported in the source material are just staggering.
We're talking about things like solving international math Olympiad problems, right?
At a gold medal level,
Right.
which is a huge leap. We're also talking about PhD level accuracy in subjects like physics and chemistry. These are not just trivia questions. They require deep multi-step reasoning.
What makes O1 different from, say, GPT-4? Is it just that it's better at math?
It's much more than math. The analysis suggests it excels at two key things. The first is knowledge integration. It can take principles from physics and apply them to a novel problem in biology. It's not just retrieving facts, it's synthesizing them across domains.
And the second thing?
Systematic decomposition. This is huge for tasks like coding. It can take a massive, complex software bug and break it down into tiny, logical, solvable chunks. It can reason about the state of a complex system. That's a step change from just generating boilerplate code.
But O1 is closed source. It's a black box. So the really exciting part for our listeners, many of whom are researchers or engineers, is the open source response. The community is not waiting around. They are reverse engineering this stuff incredibly fast.
It is a full-on chase. And the sources we've reviewed highlight several projects that are proving these techniques aren't some secret, unattainable magic. They are replicable engineering principles.
Let's spotlight a few of those. Yeah. OpenAI is one that's mentioned frequently in the text.
OpenAI is a fascinating project. They are very explicitly trying to replicate the performance of models like O1 using reinforcement learning. Their core contribution seems to be in the data generation phase. They use MCTS and process rewards to generate that high-quality reasoning data we talked about earlier. They have a specific name for their data augmentation technique, Omega PRM.
And then there's Lama Berry. I have to say, I love the names in this field.
They're getting creative. Lama Berry takes a slightly different but related approach. They focus heavily on the inference stage. They use something called pairwise optimization, combined with MCTS.
What does that mean?
They use a pairwise preference reward model to constantly compare two potential solution paths and decide which one is better at each step. It lets them dynamically refine the path as it goes. It's like having a debate partner in your head, constantly asking, is this argument better or is that one?
That's a powerful idea. And REST MCTS.
REST MCTS is incredibly ambitious. They are trying to integrate the tree search algorithm directly into the training loop itself. So it's a self-training method where the search generates data, the model immediately trains on it, and that makes the search itself better for the next iteration. It's that reinforced cycle we talked about, but implemented as a tight, unified loop in open source code.
It's amazing to see how quickly the gap is closing. It proves that the secret sauce isn't some specific proprietary algorithm nobody can figure out, but rather this general recipe. Process rewards plus search.
That's the formula. And it's expanding beyond just pure math and code. We are seeing early but promising research into verbal reinforcement search.
Okay, what's that?
This is where the model uses natural language to guide itself through the search tree. Instead of just a numerical score from a reward model, the system might generate a critique in English, like, that step seems logically flawed because you assumed X. Let's try again, but this time let's consider Y.
That seems so much more intuitive. It's using the language capabilities it already has to critique its own logic capabilities.
Exactly. Or another one is memory-based reinforcement, where agents can remember past failures across different problems. If an agent tries to solve a coding problem and fails with a certain approach, it stores that failure in a long-term memory vector.
So the next time it sees a similar problem,
it retrieves that memory and thinks, oh, last time I tried using a recursive approach, I hit a Stack Overflow. I should probably try an iterative approach this time. It's learning from experience, not just from its static training data.
this all sounds absolutely incredible, but we have to be realistic. We have to ground ourselves. What are the downsides? What are the implications of this shift?
The biggest and most immediate one is the cost of thought. It's a huge practical issue. We, as consumers, have gotten used to AI being instant and effectively free or very cheap. Slow thinking requires massive inference compute.
Every second it thinks is burning GPU cycles.
A lot of GPU cycles. If you want a model to run a deep tree search for a minute before answering your question, that burns orders of magnitude more energy and costs orders of magnitude more money than a simple reflexive answer.
It's the difference between a Google search and hiring a team of consultants for an hour.
That's a perfect analogy. You don't need a large reasoning model to check the weather. That's a system one task. But if you are trying to cure a disease or write a novel software architecture or design a new material, you are more than willing to pay for that latency and that compute cost in exchange for a much higher quality answer.
It changes the economics of AI completely. It moves us away from the race to the bottom on token price and toward a value-based model.
It also raises the question of blind spots. The sources are good to note that while these models are absolutely crushing it at math and code tasks with objective, verifiable right answers, we don't fully know how this kind of reasoning translates to more subjective domains.
Like creative writing or emotional intelligence.
Exactly. Does analyzing a poem with Monte Carlo Tree Search actually make for a better or more insightful literary critique? Maybe, but maybe not. It might just optimize for cliches.
And there's a real risk of overthinking, right?
Right.
You don't want a model to spend 5 minutes and $1 of compute deriving the first principles of linguistics just to say, hello, how are you?
Precisely. We need to know when to engage System 2 and when to rely on the speed and efficiency of System 1. The best, most useful models in the future will likely be hybrids, fast when they can be, slow when they must be, and they'll need to learn how to make that choice automatically.
And this all leads to the agent future. The sources make a very strong connection here. An autonomous agent, something like a software engineer bot or a science research bot, needs to be able to plan. It needs to reflect on its actions. It needs to correct itself when it makes a mistake.
Reasoning models are the brain that makes true agents possible. Until now, most AI agents were pretty flaky because they couldn't recover from unexpected errors. A simple API change could break them.
They lacked resilience.
Completely. A reasoning model, on the other hand, can look at a failed API call, read the error message, think about why it failed, the endpoint has changed, and formulate a new plan. That capacity for reflection and self-correction is the missing link for autonomy.
Okay, we have covered the architecture, the training, the new scaling laws, and the real-world landscape. Now, I think it is time to get speculative.
Let's do it. My favorite part.
This is our Novel Notions segment. And a quick disclaimer for everyone listening. This is for entertainment purposes only. We are taking the trajectory of this research and extrapolating it out to its logical, if slightly wild, conclusion. These are not predictions.
We're provocations. What's your first notion?
I call this the recursive scientific discovery engine. We talked about verbal reinforcement and we talked about embodied agents like robots. What happens when you put those two things together in a real-world wet lab?
Go on. I'm listening.
Imagine a reasoning model that doesn't just answer chemistry questions. It designs a new chemistry experiment to synthesize a molecule. It then controls a robotic arm to actually mix the chemicals. It uses sensors to observe the result of the reaction.
Okay, that's already starting to happen in a few research labs. That's the embodied agent part.
But here's the twist. The real-world experiments are slow and expensive. You can only run so many per day. So what I call sleep learning kicks in.
Sleep learning for robots. I like it.
The robot runs experiments all day, gathering real, physical data. At night, the physical lab shuts down. But the LRM doesn't. It spends the entire night running Monte Carlo Tree Search simulations on the day's accumulated data. It dreams of millions of potential variations of the experiments, exploring the search tree of chemical possibilities to plan the absolute optimal set of experiments for the next morning.
That is fascinating. So it's like the model is doing the look-ahead search we discussed, but on a timescale of hours instead of seconds, and using real-world physical data as the ground truth nodes in its search tree.
Exactly.
It's accelerating the scientific method by decoupling the slow doing part from the infinitely fast thinking part. The thinking can happen in parallel overnight.
The robot wakes up smarter every single morning. It's not just optimizing the next experiment, it's using the simulations to update its own internal theory of chemistry. It's recursively discovering science.
That's a powerful idea. Okay, my notion connects more to the economics, specifically to the test time scaling laws. I call it the thought economy, or maybe the compute for equity swap.
Okay, let's unpack that, the thought economy.
Right now, we pay for AI by the token. We pay for length. But if thinking time directly equals intelligence, as this new scaling law suggests, then intelligence itself becomes a utility. And it's priced by the second.
So I don't pay for the answer. I pay for how hard the AI thought about it, the duration and depth of the thought.
Correct. Imagine a variable intelligence API. Most of the time you use the free tier. It's System 1, instant answers, good enough for most things. But let's say your company's main production server goes down at 3 a.m. It's a critical business-ending outage. You hit the panic button.
I love the idea of a panic button for an AI.
You hit the panic button, and you authorize the model to spend, say, $1,000 in compute credits instantly. It immediately engages a look-ahead search with a depth of 500. It spins up 50 parallel chains of thought, running MCTS on all of them. It spends 30 seconds burning a massive amount of energy to solve your problem with superhuman precision and certainty.
So we might start trading compute credits. like a form of currency. A startup could go to a VC and say, we don't need cash, we need 10,000 hours of H100 thinking time to solve protein folding.
That's the compute for equity idea. It creates a world where the answer itself isn't the commodity. The certainty of the answer is the luxury good. The wealthiest companies and nations will have access to deeper search trees, to more thinking time.
That is a wild and slightly dystopian thought to leave on. What a deep dive. We have moved from guessing the next word to building entire trees of thought. We've gone from outcome rewards to process rewards.
The tech stack is becoming clear. Process reward models plus Monte Carlo Tree Search equals reasoning. That is the formula for the next few years of progress in this field.
And here is the question for you, the listener, to mull over. If an AI can take days to think about a problem before answering, strictly following chains of logic and constantly self-correcting, at what point does its reasoning process become indistinguishable from, or even superior to, our own human intuition?
It's a question we're going to be answering a lot sooner than we think.
The link to the main Servo paper we referenced towards large reasoning models is in the description. Thanks for listening to Talk Tensors.
See you in the search tree.